All right, here we are in lesson 9B. All right, this is again on the MPU 6050 module. Right, we've been working with a pitch and roll angle and the accelerometer, just talked about the difference between atan, atan2. And I want to follow up lesson 9A now with what's in the Freescale data sheet, right, or the application notes about restricting pitch and roll. So we had used equations 25 and 26 as an estimation of the rotation then in the XYZ frame, so in this order, right, to determine the roll angle phi and the pitch angle theta, right? And so we had then, right, here are the two formulas to remind you of what they were for the roll and the pitch angle. And we're using the accelerometer measurements for then GPY, GPZ, GPX. So that's what's coming out of the accelerometer, those raw measurements. Right? And so if you read on in the application note, right, oh, sorry, the other thing we talked about before is that equations 28 and 29 would give us then the roll and the pitch angles as well, but they used a different orientation. They used YXZ. So we decided to just go with the XYZ implementation, right? Now, both sets of these equations can provide duplicate solutions for some of the angles. Now we go back to this equation 8, which is related to which comes from the XYZ rotation, right? And it's the matrix that after you multiply the RX rotation, the RY rotation, the RZ rotation, you come up with then this rotation matrix, right? For X, Y, and Z then, right? And so if you take a look at this definition, right, and take a look at some trig identities, we can say, well, when the pitch angle is pi minus theta, right, and the roll angle is phi plus pi, when you substitute then phi plus pi everywhere for phi and pi minus theta everywhere for theta is shown here, right, and apply trig identities, well, then you end up with this solution matrix. But notice then it is the very same solution matrix. So this is equation 30, right? It is the very same solution matrix as equation 8. So what it's saying is that we can have two duplicate, so we can have the same solution for two different angles, which is not helpful, right, in calculating our position. And the same holds true if you use then equation 11 of the RXYZ rotation. So moving to that rotation does not get rid of the problem, right? And so the recommended solution from the application note is to restrict either the roll or the pitch angle, don't restrict both, to lie between minus 90 degrees and plus 90 degrees. And so that's the convention used in the aerospace sequence XYZ, and we're using RXYZ. So we'll use this convention then, we'll try this, that the roll angle has a range of minus 180 to plus 180 degrees, but we're going to restrict the pitch angle to minus 90 to plus 90 degrees. And so that will give us a unique solution for roll, right, when we use the atan2 function, right? We just took a look at atan2 and we know that it gives us angles in the range of minus pi to plus pi, which is minus 180 to plus 180. We know that atan can give us angles, right, in the minus 90 to plus 90. So we'll use atan then as our unique solution for the pitch. And so all lesson 9B does is it actually then changes the calculations for pitch and roll. Right? We've substituted then, instead of atan, we're using atan2 here. Right? And the pitch calculation remains the same as what it was, but I can bring out this. I'm going to try and let's see, load it up here. Let's see. So this is lesson 9B. By default, I have debug turned on. And so here's the only code change, right? For roll, right, we're restricting that in that range of minus pi to pi, so we're using atan2. I've also got a comment in here, so these comments have been added that we're restricting this to minus pi to pi over 2. So we'll use the atan function for that. In this case, all I've got turned on is the debug information. Right, we could upload this. Oh, and I've got to change the baud rate to match the sketch, which was 115/200. Right, so it calibrates, it shows some offset values, and right, turn off auto scroll, and then in the debug area, right, it just goes through and it shows us the calculated roll and pitch angle. And right now, mine is just sitting flat on the surface, right? It might not be perfect. This could either be error or it might not be perfectly flat. It's 0, 0. Right? All right, and so this sketch basically is the same, right, as 9A, and that if we want to plot the roll angle, right, we can turn this on, upload this. I'm going to turn on the, actually, I just turn on the monitor to make sure we're just getting numbers. We are, so we could go ahead and just turn on the serial plotter. And this is showing the filtered versus the non-filtered, right? What I don't like about the plotter is there's, I don't have a label in here, but we're going to assume since the blue is more erratic, that that is the non-filtered. And actually, if we look at the values being printed out, we'd see that's the case. And the red is the filtered. Again, to remind you with the accelerometer, if you start shaking it, so I'm just shaking mine a little bit, right, we get then quite a bit of error from the vibration. Right. And one thing you want to remember to do is if you're really trying to plot the data, debug, I had this turned down to less sampling time. Here, then I might want to really up the sampling time to 200 per second. Oh, yeah, didn't want to turn on the serial monitor. Wanted to turn on the plotter. All right, so our data is coming faster. I shake it, right? We can see the vibration. We can see the filter response. I stop shaking, right? Our filter comes back to around 0. I start twisting it, shaking it, moving it. We get some response. All right, that was the whole point then of this brief video, is to introduce then restricting the angles and using the atan2 function to do that.